Hello everyone, welcome to Diksha Karnataka YouTube channel, and it's time for me to discuss the 2, 3 and 5 marker questions from the chapter Electrostatic Potential and Capacitance. But before I go any further, I request you to subscribe to our channel and definitely join the WhatsApp channel if you want to download the class notes for all the PDFs that we are doing. The PDFs will be exclusively shared only on our WhatsApp channel, so don't forget to join the WhatsApp channel. Link of the WhatsApp channel is given in the description of this video. Also, I will like to share this video with your friends, and obviously give it a thumbs up if you like this content of this video. Now let's start. First, let us look into the questions that we are going to discuss. We are going to discuss 5 2-marker questions. We will also discussing 5 3-marker questions. We will be discussing 3 long answer type questions including derivations, and 5 numerical questions, very important. So don't go anywhere. If you want to succeed in your midterm exam, then this chapter is very essential because it's a high weighted chapter. All the questions are very important from this chapter. Without any delay, let's start with the first question. What is an equipotential surface? What will be the shape of equipotential surface corresponding to a single point charge? So equipotential surface means potential is same. So let's see the exact definition. Any surface which has the same electric potential at every point is called an equipotential surface. So if potential is same across a surface, then we call it as a equipotential surface. The shape of the equipotential surface is spherical for a single point charge. So if you consider a single point charge, then the shape will be spherical in 2-dimensional. That is nothing but circle. Try to draw some circle if you are interested along with this answer. That will be basically the completed answer. So point charge means radially same distance, the potential will be same. That's why it will be a spherical equipotential surface. Okay, the shape will be spherical in 3 dimension. On what factor does the capacitance of a parallel plate capacitor depends? Easy question. So parallel plate capacitor expression is A epsilon naught by D. So it is directly proportional to area and inversely proportional to the distance between the plates. If you are writing in a shortcut form, you have to mention this is basically area and this is D is equals to distance between the plates, right? So this is the the dependence. Next question, write 2 properties of equipotential surface. So 2 properties, very important. Try to remember 3 of them because the same question can be asked as a 3-marker question. So if 2-marker question comes, write 2 properties. If 3-marker question comes, write 3 properties. Let's see. No work is done in moving a test charge over an equipotential surface, right? If you move a charge in an equipotential surface, the work done will be 0. Electric field is always normal to the equipotential surface at every point. No 2 equipotential surface can intersect each other. The favorite of them all, right? No 2 electric field line can intersect, no 2 magnetic field line can intersect, no 2 equipotential surface can intersect. So this is the most common property across everything: electric field, magnetic field, as well as equipotential surface. In a parallel plate capacitor with air between the plates, each plate has an area of 6 into 10 to the power of minus 3 meter square, and the distance between the plates is 3 millimeter. Calculate the capacitance of the capacitor. So let's see. So capacitance of a capacitor with air between the plates is given by A epsilon naught by D. If it is not air, if it is some other medium of dielectric constant K, then you have to multiply that K over here, right? But because it is air, so K is 1 for air, so we are not adding this K, right? Now let's put the values. So A is given here as 6 into 10 to the power of minus 3. Epsilon naught we know is 8.85 into 10 to the power of minus 9. Okay, try to use the exact value here. and the distance between the plates is given by 3 millimeter. Now millimeter is obviously not SI unit, so you have to convert it into SI unit. Area is given in meter square, so we do not need to convert it, but millimeter is not an SI unit, so you have to convert it into meter by multiplying 10 to the power of minus 3. Centimeter is 10 to the power of minus 2, millimeter is 10 to the power of minus 3. So now let's cancel. One more thing, I make a mistake over here, is this is 10 to the power of minus 12, not minus 9. 10 to the power of 9, 9 into 10 to the power of 9 is 1 by 4 pi epsilon naught. Okay, only epsilon naught single is 8.85 into 10 to the power of minus 12. So 10 to the power of minus 3, 10 to the power of minus 3 cancels, 3 cancels, 2 into 8.85, 8 to the 16 and 16 plus 1.6, that is 17.7, approximately 17.7 into 10 to the power of minus 12 farad. Okay, so capacitance can be written as 17.7 picofarad. Okay, 1 picofarad is basically 10 to the power of minus 12 farad. So we have converted it into picofarad. Let's check the answer. Answer is 17.7 picofarad. Okay, now next question, define energy density of a charged capacitor. How the energy density related to the electric field present between the plates of the capacitor. So first of all, what is energy density? Energy density is defined as energy stored in the capacitor divided by volume of the capacitor. This is the definition of potential energy density. Okay, and potential energy is basically energy density, not potential energy. Potential energy density is basically half epsilon naught E square. This is how it is dependent on the electric field. Okay, now let's move on. Now let's move on to the 3 marker questions. 2 point charges 5 into 10 to the power of minus 8 coulomb and 3 into 10 to the power minus 8 coulomb. So one is plus, one is minus, are located 10 centimeter apart. Find the point between the 2 charges where potential is 0. So here we have 2 charges. This is 5 into 10 to the power of minus 8, and here it is minus 3 into 10 to the power of minus 8. Now you have to find the point where potential is 0. Okay, we have solved similar question for electric field. Now it's time for potential. Now how to do that? Suppose the distance from the first charge or positive charge is R1 and from the negative charge say R2. Okay, so and the distance actually given as 10 centimeters. So R1 plus R2 equals to 10, right? Now we are keeping it in centimeter because the unit does not matter for this particular case. If you want, you can convert it into meters, does not matter, your final result will be in meters. But if you keep it in centimeters, eventually the final answer will be in centimeters only. So this is the first condition. This is the equation number 1. Now what you have to do, you have to find the potential 0, 0 potential. Now how to find potential? Potential due to a point charge is basically KQ by R, right? For charge Q1, at this point potential is given by this formula KQ1 by R1, and if this charge is Q2, then the potential due to this charge is given by KQ2 by R2. This is R2, right? Now potential, this is the total potential and it must be 0. Okay, so K is constant, so K can be cancelled, it will be common and it will cancel, and it does not affect. Now let us put the value of Q1. So Q1 is 5 into 10 to the power of minus 8 divided by R1 plus minus 3 into 10 to the power of minus 8 divided by R2. Okay, so 10 to the power of equals to 0. 10 to the power of minus 8 will be common and it will be cancelled, right? It will go to the other side. 0 divided by any number is 0 as long as the number is not 0. So we get this as 5 by R1 minus 3 by R2 equals to 0. Okay, or let us simplify. 5 by R1 equals to 3 by R2, or 5 R2 equals to 3 R1, or 3 R1 minus 5 R2 equals to 0. Okay, this is our equation number 2. Okay, now what we have to do, we have to simplify these two equations and find R1 and R2. Okay, only one value is sufficient. Okay, so what we will do, we will multiply equation 1 with 5. So we get 5 R1 plus 5 R2 equals to 0. Okay, and equal to, sorry, not 0, equals to 10. So if you multiply everything with 5, it will not be 10, it will be 50. Okay, so 5 R1 plus 5 R2 equals to 50, and 3 R1 minus 5 R2 equals to 0. So let's add 8 R1 equals to 50, or R1 equals to 50 by 8. So it will be 25 by 4, 6.25. Okay, 6.25 centimeter. Now from where we have measured the distance? We have measured the distance. This is very, very important to mention in the final answer. The distance is measured from the bigger charge or the positive charge. So distance is measured from the positive charge. One charge is positive, one charge is negative. So distance is measured from positive charge. So you have to mention from positive charge. Right? So let's see the answer. 6.25 from the positive charge is the answer for this question. Obtain the expression for the effective capacitance of two capacitors connected in series. Parallel one is easy. I am doing the series one. Okay, parallel one maybe I will do in a future video. Only two capacitors connected in series. Okay, and there has to be some power supply. We call it a battery, so there will be some battery here. So V is the applied potential difference. Capacitance of this one is C1, this is C2. Now in series combination, okay, in series combination the charge that is flowing will remain the same. So if the charge which is passing through the capacitor C1, okay, from the conservation of charge principle, this is a closed system. So if Q charge is passing through the capacitor C1, the same charge will come over here as well, and same charge will go back to the battery. Okay, so if Q charge comes out of the battery, the same charge will go into the battery. Right? This is an isolated system, so charge has to be conserved. The total charge in this way is conserved. Okay. So in series combination, charge is conserved. Charge is same. Okay. In case of resistance, current is same. Current is also charge per time. So from that logic also you can say that charge is constant in series combination. Okay. Now we know that from the definition of capacitor, Q equals to C into V. Now if potential across this capacitor is V1 and potential across this capacitor is V2, then we can write Q is equal to C1 V1, or V1 equals to Q by C1. Similarly, Q equals to C2 V2 for this capacitor. okay, and from here we can write V2 equals to Q by C2. Okay, now the voltage that you have applied is V. Now this same voltage is divided into two parts. Okay, so your father gave you 100 rupees, you divided that 100 rupees amongst you and your, say, your brother or sister or your cousin brother, whatever you have. Okay, so you have divided this, you took 60 rupees, you gave 40 rupees to your brother. So if you add these two, total amount will remain the same, right? So basically we can say that the money that your father provided is equals to V1 plus V2. So this is the money given by the parent, okay, and this is the money that you have divided. So if you add these two, the total voltage should remain the same. Okay, now this is the first part. Now we are trying to find the equivalent case. So equivalent case means we will replace multiple capacitor with only one capacitor. Okay, so this is our C equivalent. Now in C equivalent, what is the main purpose of equivalent capacitor? Equivalent capacitor is that if I want to have this capacitor, I need to construct them by this. Okay, so actually this is our requirement and we are going via this route. This is the path, this is the road. Okay, so but what do we need? We need this C equivalent. What is the major thing about equivalent circuit? Equivalent circuit means whatever charge, total charge that was passing, the charge will remain the same. Okay, whatever voltage that you have applied, the same voltage will be dropped across the device itself. So the voltage across this capacitance will be V and charge will remain same, which is Q. Okay, so for equivalent capacitor we can write Q equals to C equivalent into V. Okay, for equivalent capacitor we can write Q equals to C equivalent into V, or V equals to Q by C equivalent. Right, now let's put these values in this equation. So Q by C equivalent equals to Q by C1 plus Q by C2, or Q can be cancelled. 1 by C equivalent equals to 1 upon C1 plus 1 upon C2. Okay, so this is the expression for equivalent capacitance in a parallel plate capacitor or any capacitor. Next, obtain the expression for the effective capacitance of two capacitors connected in parallel. Okay, parallel also we are doing. Okay, parallel also we are doing. So now let's see. Remember, one of the derivation will highly probably will come. There is a high chance that this small derivation will definitely come. There is one more derivation, 3 marker. Okay, we'll see that. So these type of questions are very common from this chapter. Now in case of parallel combination, what is same? So if you see that this battery is connected parallel to this combination, so the voltage drop across both the capacitor will be same. Okay, so this will also have voltage V, this will also have voltage V. Okay, both the capacitor will have the same voltage. So if Q charge is passing from the battery, then it will be divided into two parts, Q1 and Q2, and then again they will merge and total charge Q will come back such a way that Q will be Q1 plus Q2, conservation of charge. Okay, in parallel combination the charge does not remain same because it is getting two different paths. So from one path charge Q1 will pass, from the other path charge Q2 will pass, but you have to remember that voltage will be same in parallel combination. In series combination charge remains same, in parallel combination voltage remains same. Now let us apply the equation for individual capacitors. So Q 1 equals to C1 into V and Q2 equals to C2 into V. And if you draw the equivalent circuit for any combination will always be the same. Okay, equivalent circuit is something which is same kind of diagram. So this is the equivalent diagram. So this is C equivalent. So the charge remains same, the total charge will be same, right? The voltage applied is V, so same voltage is across this capacitor as well. So from this we can write capital Q equals to C equivalent into V. Now we will use this equation. So we will use this equation over here. So in place of Q we will write C equivalent into V equals to, instead of Q1 we will write C1 into V, and plus instead of Q2 we will use C2 V. Now V get common and they will cancel, so C equivalent equals to C1 plus C2. Okay, so this is the equivalent capacitance. This is the most easiest derivation, right? Now let's move on. Give the 3 results of electrostatics of conductors. This is a new type of questions which are given in your model question paper. So let's see. Inside a conductor, electrostatic field is 0. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. The interior of a conductor can have no excess charge in the static situation. That means all the charges, extra charges, excess charges given to a conductor will always lie on the surface of the conductor. It cannot stay inside. Derive the relationship between electric field and electric potential due to a point charge. So for that, first of all we have to draw this diagram. Okay, so suppose the potential of this let us consider 2 equipotentials. Let us consider two equipotential surfaces, one at potential V and other at potential V minus dV. Okay, one is at V, other one is at V minus dV. So what is the work done? Work done to move a test charge Q. What is work done? dW will be given by, what is work done? Work done is basically difference in potential, final potential minus initial potential, difference in potential times the charge. This is the work done. Okay, so this will be minus Q dV. Okay, suppose the electric field is E. The electric field is E. So if the electric field is E, then force is given by Q into E. And if the distance between the equipotential is dl, distance dl. Okay, if distance is dl, then from the mechanical work done, what is the definition of mechanical work done or expression? F into S, right? Fs cos theta is theta is 0 in this case, so the cos theta is 1, so dW will be dW can again be written as force into distance. Now force is what? Electrostatic force is Q into E, so from there we can write Q into E times dl equals to minus Q dV. Now Q can cancel, so from there we can say E equals to minus dV by dl. So electric field, this is the relationship between electric field and electric potential. This is the relationship between electric field and electric potential. Now remember that generally electric field is a multi-dimensional quantity, electric potential is a scalar quantity. So to relate that, we generally find only one direction of this. You can find it like this. So generally we mention that what is the meaning of that? So I say Ex is given by minus dV by dx. Okay, once you learn directional derivatives in higher classes, then you will realize what is the meaning of this. No need to write it, you can write it like this, full marks will be given to you. Now derive the expression for the capacitance of a parallel plate capacitor. I guess this is not a 5-mark question, this is a 3-mark question, sorry for that. Derive the expression for capacitance of a parallel plate capacitor. Now sometimes this can also be coming as a part of a 5-mark question. So either part of a 5-mark question or a 3-marker question. So derive the expression for the capacitance of a parallel plate capacitor. So parallel plate capacitor, suppose we have parallel plate, charge on this is plus Q, this is minus Q. Okay, the area of this plate, both the plates are area A. Okay, the distance between the plate is D. Okay, distance between the plate is D, and there is an electric field generated between the plates. Say this electric field is E. Okay, now we know that an infinitely charged plate, the electric field is given by sigma by 2 epsilon naught. You can consider that a parallel plate capacitor is very large area, has a very large area, so you can, or the distance that we are talking about is very close, so very close to the plate, this formula can be used. This is the formula for electric field. Now this is for the positive charge. Now positive charge, what is the direction? Direction of positive charge electric field is in this direction. What is the electric field due to negative charge? Negative charge will also have the same magnitude and in fact the same direction. Electric field due to a positive charge is always away from the charge. Electric field due to a negative charge is always towards the charge. Okay, negative is towards and positive is away from. So this is very, very important to understand that electric field due to positive and negative both will have the same value. In fact, because of the same direction, we are not even adding plus and minus values, everything is plus. If you consider any points outside the capacitor, then the direction will be opposite and they will cancel each other. So electric field outside will be 0 on both sides. So electric field only exists between the plates, which is very, very important. Now what is the net electric field? Net electric field is given by sigma by 2 epsilon naught plus sigma by 2 epsilon naught equals to sigma by epsilon naught, right? If you take sigma by epsilon naught common, half plus half, half plus half means 1. Okay, that's why sigma by epsilon naught. Now we have to find what is sigma. Sigma is the surface charge density. Surface charge density means charge divided by area. So let's put that over here. So you will get Q by A epsilon naught. Q by A, if you put instead of sigma, you will get net is equals to Q by A epsilon naught. Now we just did the derivation that E is equal to dV by dl. Now if the potential difference between the plates, say is V, so dV itself is V. Okay, potential difference itself is V, and the distance we already know, it is given as D. So we can write the net electric field as the potential difference divided by the distance, and that is equals to Q by A epsilon naught. Okay, or we can continue our derivation, Q equals to A epsilon naught D by D into V. Okay, now we also know that Q is C into V. So comparing equation 1 and equation 2, we can write C equals to A epsilon naught by D. Now remember, here the plate has only air between the plates. In case there is a dielectric medium of dielectric constant K, then that K will be added over here. Okay, but in this derivation K is not required. Okay, but you should remember that, especially if you are preparing for any competitive exam, definitely air capacitors will not come. Next question, obtain an expression for potential energy of an electric dipole placed in an uniform electric field. So let us do that as well. We have an electric dipole. This is also a 3-marker question. You can consider this to be a 3-marker question or part of a 3-marker question. This is also not a 5-marker question. Part of a 5-marker question or 3-marker question. Now here we have a electric dipole. Okay, we already did the expression for torque on it, acting on it. Okay, so this is the electric field E. Okay, and the torque that was acting on it was given by, torque was PE sin theta, right? P cross E, that was the formula. So torque acting on a dipole kept in an external electric field is given by PE sin theta. Here this angle was theta, right? Now what is the now if you want to change the angle, if you want to rotate this dipole by a very small angle, say d theta, if you want to rotate this dipole by a very small angle d theta, then what would be the work done? So work done will be given by the torque that is acting times the displacement. Okay, in rotational mechanics, the work done is force, a torque into the angular displacement. In linear motion, force into displacement. In angular motion, torque into angular displacement. Okay, so tau d theta is the work done. Right, now let's put the values. PE sin theta. What is P, by the way? P is the dipole moment, Q into 2A. Okay, so this is the work done. Now total work done will be given by, now to do this integration, we have to start when the dipole is at an angle of 90 degrees, start at an angle of 90 degrees, and then it move to an angle, say theta. So initial angle is 90 degrees, final angle is theta. Why initial angle is 90 degrees? We will see in a while. So PE sin theta d theta. Okay, I hope you have already done some level of integration in the class. Okay, otherwise you can check my bridge course where I have discussed basics of integration. Now PE, what is PE? PE is constant, so it will come out of the integration. So PE is out. Now what we have inside? We have 90 degrees to theta sin theta. See, one reason that people think physics is difficult, because in first PU itself the concept of integration and differentiations was introduced only in physics without much detail. Okay, once you are doing this integration and differentiation in mathematics, then this portion becomes easier. Okay, there are slightly out of sync concept, especially in PU1, and that's how your fear grows, and after one whole year of study you think that physics is difficult because you do not have the basics of this sin theta cos theta integrations, not only sin theta cos theta, integration and differentiations. Okay, so what is work done now? Work done will be PE is constant, it will come out, and so differentiation of cos theta is minus sin theta, so integration of sin theta will be minus cos theta. Okay, integration is nothing but opposite of differentiation, so it will be 92 theta. Now let's put the upper limit first. So in case of definite integration, we first put the upper limit means this one, cos theta. So nothing will change, theta instead of theta we will put theta back, so nothing will change, minus, and there is a minus plus cos 90 degrees. So in lower limit we will replace theta by this angle. Okay, so cos 90 is 1, so we get this as minus PE cos theta. Now why we took the lower limit at 90? Because this portion, this term will be 0, that's why we take the lower limit as 90. So that means, what is the meaning of lower limit and upper limit? Lower limit means this is our starting point and this is our ending point. So whenever we are doing the integration, definite integration, we start at a point, we end at a particular point. So that's how we do the definite integration. So PE cos theta is the work done. Now by the definition of potential energy, this much work done will be stored as potential energy. So potential energy is PE cos theta. Okay, maybe you will find it difficult. We will repeat this process once more when you have done the integration fully, so that you don't miss out on that thing. Now define electrostatic potential due to a point charge and arrive at the expression for electric potential at a point due to a point source charge. This is very, very important derivation. This derivation is coming year after year after year after year in your PU board exam. Almost each and every year you will see this question, and in case you don't get this in paper 1, then if you are repeating, then you will definitely get this in your paper 2. Okay, there are 3 exams, right? So in case this question does not come in paper 1, you will get this question in paper 2 for sure. Okay, now let's see that. Now electrostatic potential is defined as the work done. You can write it down, the definition is very common, so I'm not writing it on the board, but otherwise I will have short space to write. So electrostatic potential is defined as the work done to bring a unit test positive charge from infinity to a point in space. Okay, so this is how the electric potential is defined. Now I will explain that anyway, so even if you forget, it will help you to remember. So first of all, we have a charge, source charge. This is called a source charge. Say capital Q or small q. Let us say small q source charge is kept at some point. Okay, so once you have a source charge kept at some point, okay, you are trying to find the electrostatic potential due to this source charge at some point, say P on the near to this charge. Okay, so this is at a distance, say small r. We are trying to find electric potential at this point P. Okay, this is our target. Now how to do that? So definition says that to bring a unit positive test charge from infinity, infinity means which is very, 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 very far away, right? Unit positive test charge, so test charge must be +1. So if you bring a unit positive test charge from infinity to this point in space, whatever work that you are doing, that work is basically stored as the potential of that point. Okay, now basically what is the meaning of infinity? Infinity means which is very, very far. Okay, so tumba dura, For example, New Delhi, if you consider Bangalore as your home, then New Delhi is very, very far, so which you can consider to be in almost infinity. For example, I am just taking an example. Now this unit positive charge is a passenger of a local train. Okay, passenger of an express train, do not consider local train, passenger of an express train. Okay, so he board a train. Okay, he board some train which is carrying this +1 charge from New Delhi till this is our home Bangalore. Okay, this is our home Bangalore. This is somewhere before the stoppage. Okay, say this is KSR Bangalore station, this is SMBT station or Yashwantpur station. Okay, this is our actual target, but we are trying to find that what is the potential at this particular point. So the train started at New Delhi, very far away, and it's running for 1 or 2 days, and then after some time it just crossed into Karnataka. Okay, it just crossed into Karnataka somewhere say near Kalburgi or Yadgir. Okay, so it entered there and it just passed over here. Okay, this point say at a distance, this point say at a distance x. Okay, this is at a point distance at a point x. Okay, now from Kalburgi to Yadgir, this is a small station, right? They are very nearby stations. Those who don't know, Kalburgi and Yadgir are very, very near station. Okay, so so that distance between them say dx. Okay, the distance between them is dx. Now what we have to do, first we have to find that what is the work done, to move this unit test positive charge from here to here. This is an intermediate station. This is our journey is not yet complete. This is our final destination. So this is our final destination, but our journey is not yet completed. We are somewhere still about half a day to go, but we are somewhere in the middle. Okay, and we are trying to measure that. Okay, from for example, the example I was given, the train was started from New Delhi. I want to check how much fare of the each station costs. So I want to check the fare between Kalburgi and Yadgir. Okay, so how much money I have to pay. So if the train starts at here and reaches here, what is the fare of the train? Okay, so basically that is the work done. Now how much work that we have to do to bring the charge from this point to this point. Okay, this is our intermediate point. Now at this point, because infinity we cannot deal with, infinity is very far away, so infinity is beyond our reach, so that's why we took some point which is intermediate. Now this at this point, what is the force acting on this charge? What is the force acting on this charge? The force acting on this unit positive charge is kq into 1 by x square. Coulomb's force, k q1 q2 by r square. K is the Coulomb constant, q is this charge, +1 is this charge, and x is the distance. So kq by x square is the force that is acting on this charge. Now the same force we have to apply, as external force to overcome the electrostatic force. And this is a very important concept. Okay, we are applying the external force. Okay, remember that we are applying the external force to overcome the already existing electric force. This is the exact amount of electric force we are applying as external force. So this is the external force that we are applying at this point. Right now, to bring the charge by a small distance dx, what is the work done? The work done will be given by force times displacement, F into S. That is the definition of work done. So from here we can say dW equals to KQ by x square into dx. Okay, this is the work done to bring the charge from this point to this point. This point say A, this say B. So to bring the charge from A to B, the work done that we require is this one. Now, but this is just an intermediate station. We are not particularly interested in this. Our interest is to how much work that we have to do to bring it from infinity. So what is the train fare for New Delhi till KCET Bangalore? That is our target. So for that we have to calculate the total work done. So for total work done, what we have to do, we have to integrate. That is the technique. That is why first we have to construct and then solve. So construction is also upon us and solving is also upon us. In mathematics, this problem is already given to you and then you are just solving it. Whereas in physics, you are creating the equation and then you are solving the equation as well. Right? Now, kq by x square dx. Now let's understand this thing. So what is our starting point? We started at very far away, that is at infinity. So starting point is our lower limit and we are ending at this point P. So what is the distance of P? P is basically at a distance R. Okay, so this is the distance that we are interested in. The distance initially was infinity and finally the distance is R. So let's put that kq by x square dx. Okay, now definitely k and q are constant, so kq are coming out, integral infinity to r dx by x square. Now if you have followed my bridge course class, or if you have solved integration in mathematics, then this is a very simple integration. So w equals to k into q into minus 1 by x infinity till r. Okay, so this is the work done. One mistake I made, this is the electrostatic force, so external force has to be negative itself. Okay, so external force has to be negative itself, so this negative sign will be cancelled. Okay, why? Because external electric field will be opposite to that of the electrostatic force. So this negative sign indicates that the external electric force that we are applying is opposite to that of the applied electric force. And don't worry, if you forget also, like me, I forgot, remember that the final expression will do not have a negative sign, so you have to adjust that negative sign like I did. So how to do that? Only one place you can add that negative sign is to this x external. Okay, you cannot add the negative sign randomly, or you cannot remove the negative sign randomly. So negative sign, you have to apply it properly. So this negative sign has to be adjusted against the external electric force. Now you can take this negative sign common as well. So this negative and this negative will be common and cancel. So now let's put the upper limit first. Upper limit is r minus lower limit is infinity. So instead of x, we have to put the upper limit once minus the lower limit next. So if I have also discussed that in my bridge course, so if you have not solved definite integration, you can definitely check my bridge course videos. There are 2 videos where I have discussed some of the concepts, mathematical concepts mainly. So w equals to kq by r. So this is the work done. So work done that you do will be stored as the potential, that is k is 1 by 4 pi epsilon naught q by r. Remember, in the final expression you have to put this as 1 by 4 pi epsilon naught. Okay, don't keep it the final expression with k, then the teacher might deduct 1 mark. Okay, you have to put this value. Now next, what are the polar and non-polar molecules? Derive the expression for capacitance of a parallel plate capacitor. Now this one I have already done. This question I have already solved. Okay, so this is a 5 marker question where question is divided into 2 parts. One part is a 2 marker short question and another one is a 3 marker question. There is a possibility that from this chapter, this is a new type of question, okay, added in your recent last year's model question paper. So maybe you can expect such questions as well, because the electrostatic potential due to a point charge is coming almost every year. Okay, I have seen only my case is in last 10 years only 1 year that question was not there. So almost 9 years this question is coming. Okay, so maybe they are trying to replace that question with something else, so that's why I showed you this question. So non-polar molecules, in a non-polar molecule the centers of positive and negative charges do not coincide. In non-polar molecules, negative and positive centers do coincide. The molecules then has no permanent or intrinsic dipole moment, whereas in polar molecules the centers of positive and negative charges do not coincide. So even if there is no external field, so such molecules have permanent dipole moment, permanent molecular dipole moment. They are called polar molecules. Okay, so just an addition. This can come as a 2 marker question separately as well. So prepare it. Now no harm in that. Okay, a 2 marker question, a 3 marker question, they can combine it to give you a 5 marker question. Now this question is specifically for your midterm. Okay, this question I have not seen coming in for a board exam. Okay, but some students do ask me, sir, please give me this derivation. I have seen this last year also, this year also some students requested during your first quarterly test, sir, please give me this, please give me this, please give me this. So that's why I decided, okay, let me give you once. Okay, this is and in case of half yearly exam, this question did came in 1 or 2, 3 times. That's why I am decided, okay, let me discuss this. Find the electrostatic potential due to a dipole at any point. If your half yearly question is being set up by your college teachers, then there is a high chance this will come. If your half yearly question paper is coming from the district board, then there is a small chance this will come. Okay, it is not completely, even in case of district board there is a small chance this might come. Okay, but in case of if you are giving the question paper set by your college, then there is a high chance it will come. Okay, so here is a dipole. So this is a plus charge, this is a minus charge. The distance between them is, total distance is 2a. So this is a, this is also a. Okay, the angle made by this type, the point, this is the point where we are trying to find the electrostatic potential. Now electrostatic potential is a scalar quantity, so that is one good thing. We do not need to do too much of vectors things over here. Okay, so this angle is theta. Okay, now what we have to do, just be careful what you have to do in this particular case. Now remember that the point is oriented randomly, so from one side the distance is smaller, from other side the distance is larger. Okay, then we always measure the distance from the center of the dipole. So this is our distance which is given by r. Okay, this distance is r which is given. Okay, let me use something else. This distance is, say, r. Okay, so we are basically trying to find these two distances in terms of r. Okay, top and bottom distances in terms of r. Okay, that is our main target. Okay, now for that what we have to do, we have to draw a perpendicular from this point on this axis. We have to draw a perpendicular from this point on this axis. Okay, and we say that because this is a very far away point, okay, this length and this length are almost equal. That is the main trick. Okay, so these two sides are equal. Okay, up to this point. Now if we know that the total distance is r. Now what is this distance? So r minus this much, okay, r minus this much. So what is this? R minus, so that is our point of inspection, that will be main point. If you understand this diagram, the derivation is not difficult. Okay, so this side is A, this side is A, this is a theta angle, this is a 90-degree angle, right? So this side will be A cos theta. Okay, so this is A cos theta. So what is this side? This side will be R minus A cos theta. Don't worry, derivation is very easy. Similarly, if you extend this dotted line, and draw another perpendicular from this line to this, then as you can see, this is bigger line. So r, total distance r plus this much will be the length, right? Now this angle is theta, so alternate angle, this will also be theta. This side is A, so this will be A cos theta again. So this side will be r plus A cos theta. Okay, if you understand this diagram, rest is very, very easy. Okay, so electric potential due to this positive charge is given by V plus is KQ by R, in this case R minus A cos theta. Potential is KQ by R, there is no square, nothing is there. So this is the potential due to positive charge. Potential due to negative charge is K minus Q by the distance R plus A cos theta. Okay, so this is the negative charge. Now, so total potential, what is the total potential or net potential? Net potential is given by V plus V minus. Now let's put these values. So KQ by R minus A cos theta minus KQ by R plus A cos theta. Okay, so this minus and this plus multiplied and become minus. Now K and Q can be taken as common, and then we have to add these two numbers. So in the denominator, R minus A cos theta into R plus A cos theta. So R plus A cos theta minus R minus plus A cos theta. So R cancels and we get this as KQ into A plus A, that is 2A cos theta, divided by A plus B into A minus B, which is A square minus B square. Okay, now what? Now again we will just adjust them. So V total or net potential is basically given by K into Q into 2A cos theta. Okay, so Q we have taken, we have multiplied with 2A and cos theta, and in the division we only have R square. Why? Because A is very, very small, so A square will be small. So we have done some approximation that R is very, very greater than A. Obviously this is a very common approximation, right? Not even approximation, this is just a simplification, because by definition dipole of the definition of the dipole, the distance between the dipole is very, very small. So what is this? Q into 2A. Q into 2A is the dipole moment. So V total will be K is 1 by 4 pi epsilon naught P cos theta divided by R square. So this is the electric potential due to a dipole. Electric potential due to a dipole. Okay, we have done electric field due to a dipole, electric potential due to a dipole as well. So only thing that you have to do is to draw this diagram properly. Rest of the derivation, as you can see, is simple. Okay, now next time for us to solve some numericals. Calculate the potential at point P due to a charge of 400 nanocoulomb located 9 centimeter away. Obtain the work done in moving a charge of 2 nanocoulomb from infinity to the point P. Thus the answer depends on the path along which the charge is moved. So let's see, we have a charge kept at, say, at a point origin O, okay, 400 nanocoulomb. This is origin O, or let me, because people sometimes think origin as 0, you will, after few days you will watch this and you will say, sir, I don't get, you write 0 in the bottom, 400 in the top, so I don't understand. So let me simplify that. Okay, so this is point A having 400 nanocoulomb. We are trying to find what is the electric potential at this point, okay, and the distance is given as 9 centimeter. Okay, so what is the electric potential? Electric potential formula is very easy, K Q by simply R. So now let's put K is 9 into 10 to the power of 9. Charge Q is 400 nanocoulomb and the distance is 9 centimeter. Now whenever you see a centimeter, you write a 10 to the power of minus 2. Whenever you see a centimeter, you write 10 to the power of minus 2. So this 9 and 10 to the power of plus 9, 10 to the power of minus 9 cancels. This 9 is also cancelled, so you get 400 into 10 to the power of plus 2. Okay, this goes up, so you get 4 into 10 to the power of 4 volt. This is the electrostatic potential at this point. Okay, next is obtain the work done in moving a charge of 2 nanocoulomb from infinity to at this point. Okay, so now we have a charge 2 nanocoulomb which is located at New Delhi. We have to bring it to this KSR Bangalore station. So what is the fare? How much money I have to spend? So for that, now we already have done this expression for a single point charge, right? Plus 1. So for plus 1 it is V, right? For a plus 1 charge this is V. For any other charge it will be Q into V. As simple as that. For one person, I need say 100 rupees. For 2 persons, I will need 2 into 100 rupees. Simple as that. So that's why this is very, very important. So work done is basically Q into. So this is part A, by the way. This is part B. Q into V. What is Q? Q is 2 nanocoulomb. 2 into 10 to the power of minus 9, and voltage is given by 4 into 10 to the power of 4. So it will be 8 into 10 to the power of minus 5 joules. Very, very important. This is the unit of work is joules. Okay, so 4 into 10 to the power of 4 volt, 8 into 10 to the power of minus 5 joules, and obviously this is a conservative force. Conservative force means electrostatic force is a conservative force. That means work done is independent of the path taken. It is independent of the, because electrostatic force is conservative, work is independent of path. Work is independent of path. Very important statement to remember. Okay, so you have to mention that the work is independent of the path, so it does not depend on the path taken. Next, 3 capacitors of capacitances 2 microfarad, 3 microfarad, 6 microfarad are connected in series. Determine the effective capacitance of the combination. So 2, 3 and 6. Easy. 2, 3 and 6, okay, are connected in series. 2, 3, 6. So what is the equivalent capacitance formula? C equivalent equals to 1 by C1 plus 1 by C2 plus 1 by C3. Okay, so 1 by C equivalent equals to 1 by 2 plus 1 by 3 plus 1 by 6. Because everything has the same microfarad unit, so we are not adding anything else. We at the end we just need to add the unit properly, that's it. So 6 is common and we get 3 2s are 6 plus 3 2s are 6 plus 6 1s are 6. So 3 so there will be 6 by 6 is equals to 1. So C equivalent equals to 1 microfarad. So very, very important, you have to add the unit at the end. So this is the part A. What is part B? Find the potential difference across 6 microfarad capacitor if combination is connected to a 60 volt supply. Now you have connected this to a 60 volt power supply. Okay, you have to find what is the potential difference across this 6 volt 6 microfarad capacitor. Okay, now to do that you have to remember C equivalent you have calculated. So what is the charge that is flowing in the circuit? So if the charge in the circuit is Q, then Q can be written as C equivalent into applied voltage. C equivalent into applied voltage. And if the voltage across this say V1, then the same charge will pass through this as well. Voltage will be different, capacitance will be different, but the charge will remain the same. Okay, so C equivalent we have already calculated, which is 1. This is part B. C equivalent is 1 microfarad. Okay, 1 microfarad into voltage that we apply is 60. This is 6 microfarad and this one we are trying to find. Okay, so microfarad definitely cancels. 6 10s are 60. So from there we get V1 equals to 10 volt. V1 equals to 10 volt. Okay, 1 microfarad is the first part, 10 volt is the second part. Now next question. So as you can see, the numerical questions are not very difficult. It is solvable if you use step by step method. Numerical questions from this chapter are solvable, and there is a chance that you will get at least one numerical from this chapter in your upcoming midterm exam. In a parallel plate capacitor with air between the plates, each plate has an area of 12 into 10 to the power of minus 13 meter square and the distance between the plates is 3 millimeter. Calculate the capacitance of the capacitor. This is the part A of the question. Okay, so calculate the capacitance. Capacitance is A epsilon naught by D. Okay, now here they have mentioned that take epsilon naught to be 9 into 10 to the power of minus 12, so we will take that value only. So area is given 12 into 10 to the power of minus 3 meter square. Epsilon naught value is 9 into 10 to the power of minus 12. They have mentioned it, so we will take that value only. Distance D is 3 millimeter. So millimeter means 3 into 10 to the power of minus 3 meter. So they will cancel. 3 4s are 12, 4 9s are 36. So 36 into 10 to the power of minus 12 farad, or C equals to 36 picofarad. In case they don't give you this value, you use 8.85 and use your calculator to calculate the final value. Okay, even though that will be 35 point something, but because you are allowed to use simple calculator, you can calculate that. Now part B, if this capacitor is connected to a 100 volt supply. Now remember why they have given this answer, because the second part will be difficult if the 9 into 10 to the power of minus 12 is not given. If this capacitor is connected to a 100 volt supply, what is the charge on each plate of the capacitor? So the voltage is now 100 volt. okay, and the capacitance is 36 picofarad. So we know that Q equals to CV, C is 36 into 10 to the power of minus 12, and the voltage that we applied is 100. So from there we get 36 into 10 to the power of minus 10 coulomb. Okay, 36 into 10 minus 10 coulomb, or you can write this as 3.6 nanocoulomb. This is optional. Okay, if you leave your answer, you will get full marks. Okay, so answer is 36 picofarad and 3.6 nanocoulomb. As I said, this 3.6 nanocoulomb is optional. You have to calculate up to this much at least. Okay, so I hope you enjoyed today's session. We have solved 18 questions in total, including 5 numericals, 5 long answer questions, and all 2 marker and 3 marker possible from this chapter. And if you have any doubts, any questions, please don't forget to mention that in the comment section below. I'll be back with current electricity chapter next. Till then, bye.